Right, just to kick off then, nice and simple start. My name is Graham Charnley with AVK. Been with the business just over 20 years now. Used to be a civil engineer, so I can relate to some of you out there. I will stress I am not a hydraulics engineer, okay? I know a bit about hydraulics, but this is not a hydraulics presentation, nor is it a product technical training. That will follow up in subsequent webinars. What I'm looking to achieve today is to give you an overview of common issues that we see within the water and wastewater networks, and 3 of our core products that can provide solutions to these. I will also stress this is not a sales pitch today either. This is about technical solutions. Right now, I can see you all getting very excited at some of the prizes that are available. For the one that can answer the quickest on various true and false questions as we progress, there is also a £20 Amazon voucher available, but that is for another day. So, moving on then, network safety offer. Right, AVK last year were debating about how our products are being used in the marketplace and about the common problems that we were working with the different utilities and consultants in finding solutions on. And our discussions always came back to the same statement on that if you fit the correct type of valve in the right place with, and this is the important bit, with the appropriate specification, potential issues of surge, water hammer, and importantly these days, improved whole life costs can be addressed and managed at the design stage. Now, this is not a criticism of the current designs. This is merely highlighting that, for instance, if we take an air valve as an example, air valves DN 80 millimeters up to DN 300 millimeters. Wonderful. 90% of our inquiries come in looking for a DN 80 air valve. Okay, not saying that's wrong, but we can supply you an 80 millimeter air valve that will discharge 350 cubic meters per hour. Or we can supply you an 80 millimeter air valve that will discharge over 5,000.
Oh! Yeah. How much the ticket? Free? Yes, free.
Can we ask people to mute themselves?
Yeah. I was just saying there, an 80 millimeter air valve, we can supply at 300, 350 cubic meters per hour, up to an 80 millimeter air valve that will discharge over 5,000 cubic meters per hour. Massive difference, same inlet. It's all to do with the discharge capabilities of the air valve. So selection on performance is critical. That's where we're trying to come back to, is the actual technical selection based on the performance of the valves. So when we looked at the common issues, you'll all be experienced with these as vacuum, air entrapment, water hammer. I'd just like to highlight some of the dangers of entrapped air in pipelines and some of the solutions as well. So what you see here, the picture on the right, is a steel main that has suffered from a vacuum issue, and you can see that it's collapsed from its crown point down. That's predominantly because it had no air relief along that stretch of pipe. So what happened was, when the main got drawn down or discharged out, there was no air allowed back in to actually relieve the vacuum pressure within there. And the picture on the left is the analysis that was carried out, and you can see the stress point for that pipe has been right along the crown of the pipe, from failure point along. Now, this was intentional. This is a disused railway wagon, and the pumps have been set up to draw the air out of that to recreate a vacuum experience. And you can see the net effect of what happens when, worst case scenario, you draw the air out of a pressurized system. So you can see here from the other angle, you get a complete collapse of that wagon. That is the worst case scenario with vacuum.
Graham, we have a question, sorry, yes, from Adrian. He's asking, what would be the design considerations that would inform the required discharge volumes?
Well, that would vary on the velocities of your main, the profile of the pipe, and obviously the size of the pipe. What we can do, which I'll touch on later on, is we can actually provide an analysis of the main based on the inlet pressures, outlet pressures, longitudinal section, and importantly, what the hydraulic gradient is. We can then size, type, and locate the air valves for you. That would then allow you to select the correct discharge capabilities from each of the air valves. So in other words, you don't just use the same air valve in the same size along the full length of the main. You can actually select what you actually need based on the amount of air you're trying to discharge and what the hydraulic conditions are at each point. Does that answer, Adrian? Okay. Air entrapment, we talk about it, but very seldom do we actually get to see it. So what we've got here is, this is the effect of the flows along a pipe. So what you've got on the right-hand top uppermost picture, you've got air bubbles congregating along the crown of the pipe. We all know that fluid is made up of a certain percentage of air within that. And every time the flow increases or decreases or changes direction or elevation, these air pockets can be released within the flow of the pipe. So what happens is the air congregates along the crown of the pipe, and in the picture to the right at the bottom, you can see that that will start congregating at the high point and build up in size. The air pocket will continue to increase in size because it's not being released from the actual pipeline. So what you actually end up there is, indicatively, it's about 80% of the cross-sectional area. If it's a gravity main, not quite so bad. But if it's a pumped main, you're talking about higher energy costs. The pumps are going to have to run longer and push more fluid along that line to get past these air pockets. So you're talking about higher energy consumptions here as well. And as we know, air is an aggressive gas that you really don't want in your pipe system anyway, because it will start affecting the whole life of that pipeline. As far as water hammer is concerned, this is an event that happens when you have a change of velocity within the pipe. So picture number one, you've got a steady state where you've got the valve closed. The valve then gets opened and your velocities increase as the fluid passes down the pipeline. When the valve, however, gets closed, you've got a rapid deceleration of the fluid momentum, and that shock wave will transpire upstream and downstream of that point. Now, several water utilities identified this a few years ago, and there's been various initiatives by them, whether it's Always On or CAM Networks, to name but two, where they've actually started instructing their operations people and the contractors not to operate valves quickly. In other words, when you're closing a gate valve, for instance, you close it in a slow, controlled manner. And the reason for that is you want to change the velocity down to zero in a slow manner. You have the situation below that when you change, go from 2 meters per second to zero, you have the water hammer. And there is a picture of a valve, I hasten to add not ours, that suffered from surge damage. And you can see the casting is completely shattered on there. And ditto on the right, that's actually a ball check valve. And you can see from that, the shock wave that's gone into the valve has caused it to fail. So what does it actually look like when you have a surge issue? Here's a test rig in Holland that was carried out several years ago. And you have a butterfly valve that will suddenly close and stop the velocity, which has only been set at about 1.5 meters per second. You can see the test rig starting to be affected by that surge. And that surge, that inert energy that's in there, will carry on moving up and down the pipeline until it's dissipated all that energy that's in there. Now you could just see the pipe starting to move. At this end, this is changing from horizontal to vertical. And again, same scenario, the valve gets closed and you can actually see the surge moving the pipeline on its brackets here. You watch for a second, you'll actually see the pipe jumping. And that is just from a 1.5 meters per second velocity to zero. and the effect that it has on there, the energy that's contained within that pipeline, or that test rig, I should say. So you imagine that that is being affected onto older pipework that's maybe not as strong as it was the day it went in, and that's having to absorb these energies within there. More and more we're seeing older pipelines, or the age of the pipeline expanding and being asked to deliver for longer than it was originally intended. So we have to be careful with these things. Now, this was a report that was done back in 2005. We had some input to it, but it was an independent report. And these are some of the key things that were associated 15 years ago that we have to take into consideration these days. Yes, they're all valid. Number 3, the water hammer damage, we've just talked about that, particularly on older mains. The number 7, though, is something that we do have to seriously consider nowadays. We're asking our assets, our pipelines out there in the field to deliver longer than maybe they were originally intended to. So the corrosion and cavitational issues will start corroding and reducing the whole life of that pipeline asset. So nice simple diagrams. The one at the top is a typical air accumulation on a vertical drop, and you get the air pockets that start accumulating at the head of the pipeline here. It's something that we all recognise and we know we have to work on. But what you also get is, if that air pocket continues to grow and is not alleviated, it will be forced down the pipeline. And what you end up with is large pockets of air travelling along the pipe. But you also get it in horizontal pipelines or low-rise pipelines. So again, the air pockets will naturally occur within that fluid. So you have to take that into consideration. We work on a rule of thumb within the industry that if you're on a long gradual rise, you should be looking at an air valve every 500 meters or so. And again, that's getting the air out, but it's just as important to get air back into the system. There are some engineers, and I'm not saying that you're not correct, that will work on a maximum of 0.9 bar of negative pressure inside a main. Personally speaking, I like to see any negative pressure taken away, but there are certain conditions where you can live with it. But point B is a very important part, particularly on older mains, and that's the suction of seals and gaskets. If you had an older pipeline, for instance, that had corroded seals or small leaks in them, and that pipeline is under positive pressure, what will happen is the water will push its way out into the surrounding areas. But if that main goes into negative pressure and you don't break the vacuum, what potentially will happen is the contaminated fluids on the outside of the pipe will get sucked back into that drinking water supply line. Now, Professor Joby Boxall at Sheffield University a couple of years ago did a research project in this and was able to demonstrate how that actually happens. If any of you are interested in it, if you actually search on YouTube Joby Boxall, you'll actually come across that contamination of water supplies. So, what causes water hammer? Well, all you engineers out there will be getting very excited just now because you see an equation coming up on the screen. But I like to jump down to the second bottom line. And if you just remember this, for every 1 meters per second change of velocity, the pressure spike is roughly 10 bars. Now, that is worst case scenario. I'll accept that and I will not argue with it, but it's still potential to happen in the system. So when you look at it then,
interrupt you. We've just got a quick question from Stephen. Can the air valve stop back siphonage?
They can, but if they're stopping siphonage, if we're talking in a situation where, let's say, the air valve is potentially going to be located in a chamber that has flooded, let's say there's a lot of groundwater or a flood situation, a normal air valve, if the pipeline goes into negative pressure, will try to draw air back into the system. Now that air has unfortunately been replaced by groundwater during the flood, so it will actually draw the groundwater back in to the system, not what you want to happen. You can set an air valve up to have a flood guard on it, and what will basically happen with that is if the chamber floods, it will lift the flow up and seal off the inlet to the air valve. When the flood waters go down or you pump the chamber out, that guard will drop and the air valve will be allowed to draw air from atmospheric pressure. The problem, if you want to call it that you'll have is, whilst you're in flood and it's not allowing air back into the system, you are creating a scenario where there's no vacuum break. So it's a case of a temporary negative or a temporary contamination issue. That's a risk and balance that the utility has to decide on. What I will say is that we have not sold that many flood guards to air valves. We have had conversations, particularly with one utility that's got a lot of low-lying ground with a high water table. And what we actually advise them to do is to pipe the outlet above the level of the potential flood levels. That's fine if you've got somewhere to take it to, but if you're in the middle of a field or a country, you don't want large vertical risers for the air outlets. So you have to think about where you're locating those air valves. But remember, after the discharge point of an air valve, it's atmospheric pressure it's working with. There's no pressure build-up on that piped outlet. So you can look at piping the outlet to a safe air location. Okay.
Thank you, Graham.
So just to follow up on that, typical example means a 3-bar system with a 1 meter per second surge could, and I stress the word could, cause a 30-bar pressure spike. This is worst case scenario, as I've said, but this is why utilities are trying to slow down the operation of valves, and why as designers and suppliers we're trying to help overcome potential water hammer or surge issues within pipelines. Because when you have a pressure spike, it's effectively a localized punching effect into the network. So you can't get away from pressure spikes, particularly on pump systems, because you're putting energy into a pipeline and then suddenly you want to stop it. So the pump manufacturers are looking more and more at controlled shutdowns or slow startups, slow shutdowns. You're looking at operating the valves in a manner that doesn't help to create pressure spikes. But this isn't just about the utilities or the operators on the systems. You're also talking about the fire brigade when they come along to operate a fire hydrant. And I use the term fire brigade because we all know there are other companies, shall we say, that have access to hydrants that shouldn't really. But every fireman I know and have met, always the same. It's always the youngest fireman that gets sent along to operate the hydrant. And he's always wanting to show off how fast he can operate that hydrant. So he will crack the hydrant open as fast as possible to get flow. Again, that's good for their needs, but it's bad for the utility because you'll get a sudden acceleration in flow, which will potentially cause water discoloration, but you'll also create that surge scenario that we're talking about. So, assuming you've all paid attention, true or false? A 1 meter per second change of velocity equals a 10-bar change in pipeline pressure. Is that true or is that false?
False.
Well, you don't need to tell me. You need to write it down so that we can record that and then decide if you're going to win a prize or not.
The chat function isn't working.
Bugger. Well, it looks like everybody's getting a £20 voucher. No, I lie. I take that back. Okay. I stressed at the start that this is not a technical presentation on the products, right? My intention is to follow this up with a dedicated webinar on air valves, one on check valves and one on control valves. But for now, just to give you a slight insight into where we are coming from, we believe the air valves, they ensure the system operates with optimal efficiency. Why? Because it gets the air out of the pipe, giving you a full clear bore to operate with. It reduces pressure build-up. We talked about that earlier on. We talked about the problems with vacuums. And by doing all of these things, by managing the air within the system, you end up with the asset itself, the life on it can be extended. Same report that I referred to earlier on, I would love everybody to put them in every location listed here. The reality is I've been in this industry since 1984, and I have never seen air valves put upstream and downstream of a line valve. But it is important to have them at pumping stations after the pump and after the check valve. Again, I'll show you in a second why that's important. End of lines, it depends. If it's a free end discharge, no, it's not needed. But think about it, if it's coming into a controlled environment, say a water treatment or a wastewater treatment plant, if it's going into another pressurized system, you should think about getting the air out of it before it goes into the processes. Now, nice and simple one, there are only, whoever manufactures them, 3 types of air valves: an automatic, a kinetic or large orifice, or a combination. I say that there is a 4th type, and that's the non-slam type, but it is in effect a development of the valve that you're seeing here. A kinetic valve on the right, or large orifice, its only job is to get rid of large volumes of low pressure air from a pipe system, usually when it's starting up. When you're draining it down, it brings the air, gets drawn back in and breaks that vacuum. The automatic air valve is exactly what it says. It continues to operate automatically, discharging air once the system has been pressurized. And the combination is exactly that. It is what it says in the tin. It's a combination of the kinetic and the automatic. Now, what you've got here is a typical scenario where you've got a pump system operating with a check valve upstream of it, pumping up to a control point at some stage with a pipeline that varies up and down. So the pump operates nice and evenly, kicking out 15 bar pressure. My God, that's a lot of pressure. But when it stops, when the pump trips, there's kinetic energy within that fluid that will carry on going up the pipeline. You created a vacuum behind the check valve, and if you don't have an air valve to release that air and break the vacuum, you'll end up stressing the pipe. And you do that enough times and you end up with a failure of the main. Now, this is a new valve that we're bringing onto the marketplace, but for intents and purposes, it's a double orifice air valve with a non-slam device, the black disc you see there. So as the air is being discharged, the velocity, the higher velocity of the air lifts that disc up into the closed position and limits the amount of air being discharged. So what you're doing is you're releasing the stress, you're using the air to help balance the pressure there. Automatic orifice in the center there carries on discharging while the main is charged up and under pressure. However, when the main draws down, the disc, the non-slam disc, is now dropped into the open position. The fluid drops, the float drops, and then under atmospheric conditions, you can now draw air back into the pipeline and break that vacuum and stress. And these valves will carry on working automatically on their own with minimal input. I say minimal input because, like any operating part, they will need servicing. Once a year, once 2 years, every 3 years, we'll see. So what you've got here is the kinetic energy of the fluid is still going, but the air valve is allowing the air to be drawn in, limiting it on the way out, which helps to dampen down that energy that's in the system. What it also does, because it's downstream of the check valves, it stops that event of the hammer going into the check valve. So that's fantastic, wonderful. But does it actually work in the real world? Well, these are a couple of examples. This is a brine site, and you can see the existing asset on the left. And brine is a very, very corrosive fluid to deal with. So I got involved in this many years ago, and the solution that we came up with at the time was a wastewater valve on the right. But a standard wastewater valve would have suffered the same with corrosion. So we actually went for a stainless steel 316. Lovely and shiny, wonderful. It's good for the end user now because we've actually developed it into reinforced nylon, which is completely non-corrosive. So as a result, the cost of that have actually reduced significantly. This is an interesting one down at a utility I work with, where it's within a treatment works system. But what was happening, it was coming from low level up, across, and dropped back down. So the pump started pumping, and then when the pump stopped, there had been a vacuum created within that pipe that caused the flows to carry on. But you wanted rid of the air from the pipe when the pump's working. So what we actually came up with here is you've got an air valve on the top to get rid of the air when you're running. But when you want to actually break that siphon effect, we developed a solenoid operated butterfly valve to the left there. And that opens when the pumps trip off, that breaks that siphon condition, that stops the flow continuing after the event of the pumps switching off. And for those of you that are working in treatment plant design, this is something that you need to be aware of, because you tend to have very low pressures within a pump system inside a plant, but you still need to manage the air. That's a sewage air valve, and for those of you that are looking closely, we'll call it waste material has flown down the outside, because there wasn't sufficient pressure to actually close that valve off now. Fortunately now, we had a solution for that, where it actually valves seal at 0.05 bar pressure. So again, that valve wasn't suitable to be used internally. We swapped them all out. That was the solution to it. And finally, I would beg, when I turn up on site and I see all the pipe work, lovely roasty toasty in the thermal jackets, and the poor air valve sitting up fully exposed to the weather elements, remember you have stagnant water contained inside that air valve. So you need to protect that from the elements as well. The good thing is we have a whole range of thermal protection jackets that can come along with them. So please think about the thermal insulation of the exposed valves as much as whether it's through trace heating or thermal insulation on the pipe work. And AVK sometimes is accused of being difficult to deal with, and that's only because we ask so many questions. But this is the information that we really need to be able to size and type the air valve for you. If you can give us all 9, fantastic. But the reality of it is there are some key areas that we do need to understand if we're going to optimize and give you the best efficient solution for what you're looking for. If it's any supplier of any type of air valve, you should be getting asked all of these questions. So again, the more information you can give us, the better and more efficient system we can help you to deliver. So, or false. Air valves are optional on pressurized systems. Is that a true statement or a false statement? Anybody that gets that wrong, I will be down to firebomb your office. But please take that as a joke, it's not intentional. Right, I just want to touch on non-return valves. And the reason for this is there are a massive variety of non-return valves out there. You would always expect to see them on the downstream side of, the upstream side of a pump to protect that asset. But the reality of it is, even AVK, we can offer, 7 or 8 versions of that in basic principles, but then the specifications can change internally to them. So you'd want to see them downstream of pumps. You'd want to see them wherever you're looking to reverse flooding conditions. You'd want to see them theoretically where they're going into industrial sites. Now, I will stress that this is not backflow prevention in the true sense of backflow prevention. Yes, it checks flow and it stops it from flowing back along the main. But if you're going into true backflow prevention, that's a completely different type of product here. So this is more to stop the reverse flow after system shutdowns.
Graham, just a quick question from Tim. For the anti-surge air valve,
yes,
are AVK able to provide the operating characteristics for inclusion in a surge analysis model?
Yes, 100%. We have full flow graphs available on every type, and there are at least 8 different types of non-slam check type air valves, and we can show you the flow characteristics in all of them. Okay. Okay, so check valves. There is your basic check valve, whether that's metal faced or resilient seated. You've got your plain spindle, you've got it with lever and weights to help on closing or opening performance. And obviously anywhere you've got a moving part, you should guard against it. I said you can get metal faced or resilient seat. Absolutely. Those are the two main variations. There was always a philosophy that metal face was for wastewater and resilient seat was for clean water, and that applied to check valves and gate valves. That is not the case. Resilient seat valves can be used in wastewater applications. With this AVK check valve, you do get a 100% clear bore when fully opened. And again, that's something for designers to bear in mind, is what is the actual opening position of non-return valves. Because if you move on to the wafer check valve, that's a non-return valve, but you can see the head loss through that will be a lot higher because you're not going to get a full clear bore on there. What you have is you've got springs on the back face, and that valve gets sandwiched between two fixed face flanges. And then it effectively operates like a butterfly, where both sides will get forced open, resisting against the springs, and close again. You've then got the recoil check valves. A company that joined the AVK group back in 2001, I think it was Glenfield and Kennedy. And Glenfield are known for actually developing and bringing this valve to the marketplace. I think it was 1940s, 1950s, maybe even before then. But the recoil check valve is very much related to the hydraulic conditions of the main, where it's a fast-acting check valve, and the body of the valve actually starts to absorb some of that energy when you've got surge coming back down the pipeline. And the larger sizes, it actually moves on to multi-door valves. And again, these are all fast-acting. And the reason that you've got to have multi-doors there as opposed to just having one door, like you would have in a large diameter standard check valve, is you've still got that speed of closure that you're looking for on that valve. So hence the fact, if you went for a full-size door, the speed to close would be so much, well, I say so much longer, it would be longer than if you kept that main cross-sectional area for each of those doors. And then you've got nozzle check valves. This is a relatively newer product for the last couple of years to AVK. But again, it's a different scenario. You've got a different methodology of closing. And effectively, you've got a spring-loaded plunger contained within the body of this valve. But again, you can see it doesn't have a full clear bore. You've then gone into hydraulic solutions, silent check valves. You get tilting checks, slanted seat checks, ball checks. You've got lots of different solutions to effectively the same problem. In other words, stopping reversal flow. And all of these valves can offer the solution depending on what the hydraulic conditions are. And this is where this network safety solutions is looking to bring focus, where we're not just talking about selling a product, we're talking about solving a problem or solving a hydraulic condition.
Graham, just on the recoil valves, question from Stephen. They're able to be used in sewage systems, aren't they?
Apologies, I overlooked this last time. No, the recoil check valve is intended for water supply only, water and raw water, not for wastewater. Okay. Practicalities of the application of these are ball check valves used in a wastewater treatment plant, and you can see that they've easily been put in the vertical, cutting down on floor space required. Your standard check valves, I wanted to show this picture because something that you should always consider is you're looking at 5D from a change of direction or an asset like a pump before you reach the non-return valve. That's so that it allows the check valve and the flow going through it to have some semblance of a lack of turbulence. So it goes through the check valve in a consistent flow. Engineers here, I like using this picture as well, because my challenge always is, if I was an operator and I had to get up to maintain that valve, what is my access like? And right there, I would not fancy putting a ladder against the pipe to get up to access it. So please think about future access for maintenance of these products as well. This picture I do like, excuse me, and this is actually a UK installation, where you can see you've got your check valves and you've got 5D from a change of direction to the point of flow through. You've got air valves on the downstream side, nice and cozy in their thermal insulation jackets. And the gate valves on the right, you can see that we actually added a solution there as well for ease of operator access. So that's a well thought out, well installed installation aspect to these products. And again, it is important to understand that the maximum flow through your standard check valve is 4 meters per second. There is a minimum velocity and a minimum pressure to actually open these as well. But again, this is the reason why we ask questions from you. But just remember that a maximum of 4 meters per second. And because my memory is quite bad at the best of times, we put all these things into a relatively easy to read chart. So you've got where it can be used, what the minimum sealing pressure is, and what the minimum velocity through the valve is, but also the maximum velocity, where it can be installed, etc. So, as I said, this is not a technical presentation. This is opening the door to driving a bit deeper into it. So, true or false? The maximum flow on standard check valves is 4 meters per second. Is that true or false? For those of you that are still awake, I'll like to see your answers. And then finally, just moving on to control valves. We have diaphragm valves that you can use for control. We have needle control valves. You can use the diaphragm for a multitude of applications. And you've got your needle control valve for much more accurate flow controls. A typical arrangement we should be looking at, where you've got your diaphragm control valve on your right, you should be looking at isolators upstream and downstream for future maintenance. You should be looking at an air valve on the upstream side, because diaphragm valves don't react well to air pockets going through them. And you should be looking at strainers on the upstream side. Again, diaphragm valves and the pilot systems don't react well to having debris going through them. You could argue that the UK water industry, the water is of good enough quality that you don't need it. However, I used to work for West of Scotland Water, and I saw a lot of water supply pipelines, shall we say, that were getting taken out for replacement. And the build-up over the years was such that any change of velocities could lead to discoloration. In other words, debris floating about inside the pipe. So that could potentially lead to your control valves being affected by that debris. So then you've got your control valve. So why do you use them, and where do you want to use them? Well, obviously the basic default for a control valve is changing pressures. But you can also use them for a number of other things, from inlet to process plants to controls on pumps. But ultimately, every control valve composes of effectively two components. On the right, you've got the main valve, the ductile iron body of the product. And on the left, you've got the pilot system, or the brains of the outfit. And it's through that pilot system that you actually set up the controllability of that valve. So this is the important part. Please remember this. If you've got a 250mm main and you want to set up some controllability on that through a diaphragm control valve, it is the flow that you're looking for that is important, not the size of the pipe upstream and downstream. So in this scenario, with 190 cubic meters per hour on a 250mm main, you actually need a 150mm control valve. Now, on a control valve, you don't get good controllability in the first 15 to 20% of movement in these valves. So what you actually want is you want the valve to be 20% or more open to have that controllability in there. So you don't want to have that the flow is limited by that initial opening. All that will happen is the valve will regulate poorly. So we would recommend a 6-inch control valve there based on the flows required. If you go for a 250mm, it will still work. It will still give you some controllability, but what will happen is it will constantly be searching, it will constantly be moving. And because you're only open less than the 15% initial, what you'll end up with, again, potentially, is causing cavitational issues on that valve, which will end up not giving you the full life that you're looking for from the valve. If you think about how you size meters, you can apply the same principles to how you size control valves, i.e. what is the flows that you're looking for through that product. So we don't recommend that you size based on your pipeline, but what you're looking to achieve by that valve. And as I said, there's many different types and styles of these control valves. But another control valve that's come into use is the needle control valve. It's a completely different design where you've got the flow passing around the outside of the internals and the sealing happening, as you can see on the red dots there in this animation. This gives you much more controllability. And on this video animation, you can see bottom right where the flow is actually going. So in other words, it's coming round the outside and being forced down into the center of the pipe downstream. That's what happens when the valve starts to close. You effectively reposition the internal piston, I call it, into a position that you want to have the controllability and flow rates on that product. And again, like every product, there are many variations from hand operated to actuated right through to hydraulic. And we will ask you questions on these things. Like any control valve, common types of them you'll all be familiar with, whether it's from an eccentric, a globe or a ball valve. And some that you might not think about as a control valve. Some people think butterflies are just on off. Again, with the principle of a percentage opening, you can use them for controllability. And knife gate valves as well, we can supply you these with, or these can be supplied, I should say, for flow control, but not standard knife gates. And for those of you that are thinking, well, that's brilliant putting in all this, these new products in there, but we're trying to move down the path of it being a smart network. Well, 18 months ago or so, AVK launched their package of smart control, and all of these products can be linked in. I am not the best person to talk about this. It's one of my colleagues, a chap called David Hurley, and he's actually, like many of the utilities these days, he's actually undergoing various trials in the UK for demonstration purposes and for the future, smarting up the networks, if you like. So, final question. Control valves are sized based on the main diameter. Is that true or is that false? Lied. But how many of you actually stayed awake through all of this presentation? Was it 2 of you or was it all of you? I think asking or mentioning prizes at the start should have kept most of you engaged. But thank you very much. That's me finished on this overview. As I said at the start, I am looking to follow this up with specific technical presentations on air valves, then another one on control valves, and then finally one on check valves. So this was really just to give you an awareness of what AVK are looking at, where we see the problems to be, and where we see potential solutions to be for these as well. So thank you. All done. Do we have any questions from anybody? Or are you all just keen to go and get a fresh coffee?
Not getting any questions at the moment, Graham, but it might be a good idea just to go run through the answers of the questions, just to put people's minds at rest.
I want to keep them excited. Well, obviously the last one there, it was everybody stayed awake. control valves are based on the pipe's main diameter. That is completely false. You size it based on your flow rates that you're looking for. The maximum flow in check valves is 4 meters per second, on standard check valves, I should say. That is true. We can supply, or there are check valves available that can deal with higher velocities, but on standard valves it is 4 meters per second. And air valves are optional in pressurized system. That is false. They are required on any pressurized system. And a 1 meter per second change of velocity equals a 10 bar change in pipeline pressure. That is true. And now all the hydraulic engineers are going to jump all over me and say that I am false.
Hi there, Graham. It's Kate from the Guild.